All right, party people. This is class for Thursday, March 21st. Here's what we're going to be talking about right here today. I'm going to get your quizzes back to you. That's tomorrow for me. So we'll just say today. Now that it's Thursday for y'all. If I forget to say it in the email, Ms. Barron, please give them their quizzes back. Anna already has them. Grab them from her. I will try to remember to type that in an email here in a little while, but I may forget. So pause me or run out while I'm talking and grab those so they can have those to look at and see what they missed. And let me know any questions this weekend as you guys are preparing for the test. Okay, so you should have those back. I tried to make little notes if you guys had questions that arose in there. Let me know if you have any further questions, what you didn't understand. I may not have made as extensive notes as you need to adequately deal with any misunderstandings or whatever. Okay, so just let me know about that. So you should have those back now or in just a minute. Then we're going to go over the CO2 homework. We have some unexpected results on that one for me. I'm still a little confused. I'm going to work some additional problems, I think, this weekend and get those out to you so that as you work them, you can check and see where you've gone right or wrong on them, and you won't be surprised when some of those show up on the test, and you should be able to do them. Brings us to test on Tuesday. Don't forget, get prepared so we can start off with a good grade for the final quarter here. We don't have too much longer, so let's really give it a good effort and really prepare for each and every assignment that you've got. All right, we're going to lecture 10.1 today, and really this is just kind of to fill the space. I mean, it's stuff you're going to be tested on, and we're going to do it, but I'm not lecturing on it today for any reason other than to give us some separation between finishing your homeworks, getting your quizzes back, and giving you a little bit of time before your test to prepare based on your quiz grades. So I'm sorry I didn't get those back to you faster, but we had a couple people trying to wait for them to finish, and now we're where we got to get them back. All right, so we're going to run through this CO2 homework just to kind of give you an idea about what, how we might run real calculations in real life. All right, so let's look through that. And that dude was super nerdalicious. He makes me look like a non-nerd, I guess, which is pretty hard to do. But that dude definitely did it. Okay, so if you don't have your homework, boo hiss, you should have your homework. If you got it, please get it out. If you don't, just maybe take some notes on how these were worked, because this kind of question might be something that I would put on a test, because this is good creative thinking stuff that you guys need to be working on. All right, so area of one of the faces, that's pi r squared, okay? And you should, did I ask you to keep it in inches squared? Well, I didn't technically, but there's no reason you would have thought to convert it. So hopefully you work those in inches, and if not, you can just rework it in inches. It's not that big of a deal. We're going to have inches cubed later. You might have noticed that your R is in inches cubed, so that might have tipped you off to just stay in inches. So you should end up with 7.07 inches squared. Okay? And calculating the volume of the interior of the chamber. And again, any of you who came to the ACT review, we talked a little bit about this, but anytime you've got a shape, and it works for these two. And that's not just a bad cube. That's supposed to be a trapezoid solid, trapezoidal prism. Any of those. All you do is you get the area times the height. Okay, so any of those prisms is what those are called. Okay, you just get the area, you push it through the height, and that's your volume. Okay, and just as an aside, I think, again, we've talked about it, but you take that's the center, take a radius there. It's just 4/3 pi r cubed. That's the volume of a sphere. Just always a good thing to reiterate those, just to maybe lodge them in your brain somehow. And by the way, this comes from from calculus, and it's really cool to see that volume is the integral of area. It's crazy, and it really kind of hints at how powerful calculus is. And hopefully you guys will study that at some point, if not at St. Augustine, then in college. I highly encourage you because it's really cool stuff. All right, anyway, so how do we get that? We get our area, which we had right here. We just solved for that, so we just bring that down, and then times the height. I went ahead and converted it to inches for you, since I was kind of making up the numbers anyway, guesstimate based on the video, and we should have gotten this volume right here, 5.3 inches cubed. All right, and I think he actually says this out loud, and you can see the gauge a couple of times. It's about 700 psi. That's just a fact. There's no calculation there. All right, beginning temperature. You can see the temperature on his little multimeter thermometer thing there. Converted to Kelvin. He should have gotten 297.15. All right, and so at the beginning, the force that exerts on one of those faces is unbelievable. Okay, so 49 newtons is what I got when I did P is equal to force divided by area. You multiply this across, and you end up with 49 newtons, which is, we'll just, for round numbers, well, I can't do that off my head. I was thinking 2.2, but that's kilograms to pounds. Anyway, that's a lot. That's a lot of newtons there. Actually, I can do that. Let's see, it's about 500 kilograms. So that's about 1,000 pounds of force that gas is exerting on that face. So you can see why he made it so thick. All right, and so he kind of talks about the supercriticalness, how it had a clear liquid and a liquid and gas state. You could see the liquid sloshing around in there. And then at some point, it just sort of, the vapor became denser and sort of matched the liquid, and then they sort of stopped being divided, which is kind of weird, but I thought it was really cool. I'd never seen it before, and I've been trying to think of a way to really get this in to let you guys see that coolness too, and I finally had an excuse with pressure and the gas laws. So anyway, so what, kind of whatever you put there, that's just kind of a, were you listening, were you watching, okay? And Ada kind of let me know that y'all may have been having some trouble. I guessed it was 1,000 psi. He doesn't actually say it, but you see it a number of times in there, and the black numbers, not the red ones, were what they were. So I just kind of said 1,000 psi approximately. So where did that come from, right? So he heated up the gas, and we see as temperature goes up, no, I was about to do temperature and volume, so never mind. But as temperature goes up, pressure goes up, and we could derive that out from the ideal gas law. Maybe we'll talk about that in a second here. Well, we could do that. So if we hold all these constant, V, N, and R, which this is a constant. The number of moles in there stays the same, and the volume doesn't change. That makes sense. We can essentially we can put all the constants on one side, and we just end up with P over T is equal to P over T, which when it's set up like that, we know that as this one goes up, that one's got to go up, and this goes up, and that goes up. Okay, and you could plug in numbers if you wanted to verify that. And we sort of did that with this here in a second, but as we'll see, the numbers didn't quite work out. All right, so is that gauge pressure or absolute pressure? Well, how do we know? Well, the only way we would ever measure absolute pressure is if we were out in space, or you had something that corrected for the atmospheric pressure. But in general, anything you're reading is going to be a gauge pressure. And so when we've got a gauge pressure, we have to add an atmospheric pressure to get our absolute pressure. You guys did that on your quiz, and I think everybody maybe got it. I'm trying to remember. I think everybody got it. So we just add those together, and we get here. And we see that in this case, because it's 1,000 psi and atmospheric pressure, and which you may have just had to look that up. I had to look it up. I don't know if it's in your book or not. I don't remember. I just Googled it. You can see that doesn't make that big of a difference here, but it's what's the total absolute pressure there. I wonder if maybe that's why some of my numbers, I just used the gauge pressure instead of the atmospheric pressure. Well, we'll talk. Let's see. Maybe I'll have a second to run those numbers. All right, so then at 308, I just asked you what's the temperature, and it was, I noticed actually, and upon rewatching, that it was a little bit closer to maybe 37 or 36. But again, we maybe would say 309. Okay, it's not a huge. We saw as the temperature dropped, the pressure did not drop significantly. Just later in the video. So, and then I just asked you the number of moles that must be contained in the vessel. And PV nRT, we had a P, we had a V, we had N that we're looking for, an R and a T. R, I just looked it up and gave it to y'all. That was not one of the ones that was provided in our book. Needless to say, if I asked you that on a test, I would not ask you to memorize that number or know some weird number. And I'm just really fast gonna run this with what do we say? It was 14 psi was the so let's run this and see how much that affects our number, and then if that matters. All right, so really fast, I'm just gonna run that. So 714 times 5.3 divided by 73.59 divided by 297.15. Okay, so that gives me, I don't think that's going to fix my problem. My second answer here is 0.173 mole. Okay, and we'll check the other one too, but I don't think it's going to save us from our confusion here. All right, so then we looked at the second temperature, the ending temperature here. What do we got? We got 1,000 psi, 5.3 inches cubed, 73.59, 306 K. And I'm just going to, for the fun of it, 1014.7 times 5.3 equals N, 73.59, 306. Yeah, that doesn't fix our problem because this number goes up as well, and that becomes 0.252 moles. All right, so we just got an issue, and I'm so this was really just an opportunity for you to think through this. Okay, and they're close but not great, so we didn't get like 15 moles and 0.1 moles, but we did get a pretty significant change, which was 0.235 or 0.252. Versus 0.169. And so let's do a percent error on that. So we have 0.169, which is an absolute value, minus 0.235 over 0.169, because that's our expected or our predicted. All right, and so that's like a 40% error. Okay, and that's the answer I got, right? So 0.39 or 39% error. That's not super great. And I really have no idea why that should have been the case. I mean, we expected the pressure to go up when the temperature went up, but it didn't do at all what it seems like it should have. And I went and back calculated what the pressure should have been at that temperature of the ending temperature of 306, and the pressure should have been 718 psi, and it was at 1,000. And so I'm wondering if maybe the pressure wasn't as high as it could have been because part of that CO2 was liquid at the beginning, and it then sort of all became a gas, which means that it wouldn't have been obeying the ideal gas law at the beginning. And so I'm thinking that has something to do with it, in that only a certain number of those moles were sort of exerting that pressure. But without really being a lot more familiar with how things work in a closed container like that, as you heat them from one phase to the other, and I've got no idea. So we'll just kind of be in the dark about that together. But it's good to know, hey, look, we were doing something wrong, right? So like you can start looking into stuff, and then this could be really an interesting endeavor to start looking into. Like, all right, so what would happen if I raise the temperature of water so that it transitioned from completely in a liquid to completely in a vapor phase? What would the pressure do? And then you start looking into it, and maybe you learn something cool, okay? So I love stuff like that, and that's why I really like XKCD, because he does that kind of stuff all the time. So anyway, maybe I am as big of a nerd as that guy. I guess it's possible. All right, so to keep us moving forward, keep us from kind of bogging down here, we are going to push on into chapter 10. All right, so don't turn your brain off just because you're focused on chapter 9. Okay, this is stuff that we're going to need to know, and it's stuff that we're going to be tested on, and the sequencing is just a little bit different than what we've been doing, because I'm trying to give us some more time to discuss homework and problems and really get you guys comfortable with concepts and being tested on them before we have a test. Okay? All right. So you guys were supposed to read and annotate, and so I have done that. And so here we go. This is solution chemistry. This chapter is, as you see, low solution chemistry. And basically that's just stuff that's happening in a liquid phase, in a solution, right? So a solute is dissolved in a solvent, okay? And this is a big kind of a fancy, to me, sort of seems like a fancy word, like, ooh, we're doing solution chemistry now. That's must be complicated. It's really not complicated as soon as you kind of figure out what we're talking about. All right, so what we're going to talk about today is section 10.1. We're going to describe the process of dissolution of an ionic solid, acid, or base in a polar solvent, such as water. And if you guys remember what polar means, great. And if you don't, I will briefly touch on it. Use energy concepts to explain how the heat of solution might be positive, indicating endothermic, or negative, indicating exothermic. Describe entropy. Define electrolyte. And distinguish between strong and weak electrolytes and account for the difference. Okay. And we are basically going to graze these topics. Okay, these are topics you can spend months on in a college inorganic chemistry class. Okay, we are not going to do that. We are going to skim through these. Excuse me for the camera here. I hope it's not making you car sick. All right, good deal. All right, so this first part is going to be a little vocab heavy. So kind of note that difference. The gas laws are pretty math heavy, and that's not the case, at least right now in this chapter. All right, so things to note. We got Arrhenius, and he is the guy that did a lot of work on solutions. Okay, he actually has one of the definitions of acids. There are a number of different definitions of acids and bases and how they act and what distinguishes one kind of molecule, whether it's an acid or base, from the other kinds of molecules. And Arrhenius ended up with one of the definitions, and it's still sort of referred to that way. It's an Arrhenius acid. Anyway, so I don't know if he touches on that later on in the book or in this chapter, but just know that he's one. So maybe give him a little underline there too. Okay, process of dissolving. Literally, that's just the definition of dissolution. Okay, so dissolving and dissolution. But note that I have it underlined, so that might be a good thing for you to do, so that when you're looking back and thinking, I wonder what words from the vocabulary might show up on a quiz. Wonder if I underline that. Oh, look, I did. Okay, so y'all be underlining. All right, solvent, solute. You need to know what those are. Solvent's the thing that does the dissolving. The solute's what gets dissolved. And if that happens, that solute in a given solvent is soluble. Okay? So these are all words you should be at least partially familiar with. I can't remember offhand now whether we have talked about it specifically yet or it's just getting introduced now. All right? Water is often called the universal solvent. What does that mean? It dissolves a lot of different things. Okay? It doesn't dissolve everything. Okay? It is polar and it tends not to dissolve non-polar things. Okay? So it really likes polar molecules and it can do a lot to dissolve those, but non-polar ones like oils are immiscible, which is the opposite of miscible. Okay? So substances that can dissolve in a solvent in any proportion are miscible. All right, so what does that mean, in any proportion? That means like you can basically put as much of that thing in the solvent, as much of the solute in the solvent as you want. So much so that you can't even really properly say that one's a solvent anymore and one's a solute. So example, if I have 100 milligrams, 100 milliliters of ethanol and 100 milliliters of water, I mix them, they completely mix so that you could not separate them except by like boiling. Okay, so it would be a complete mix between the alcohol and the water. You could put 1,000 of this and 100 of that, or 1,000 of this and 100 of that, and they'll completely mix. Okay, so like we'll talk about solubility here throughout this chapter. You can't do that with everything. Lots of things have a certain amount that they will dissolve and not anymore. Okay, so those things are not miscible, they are soluble. Okay, all right, so again, note it's underlined. Should end up underlined in your book. Dissociation. Okay, they're not associating with one another anymore, so they're dissociating. They're separating. All right, so what happens here? Let's say this is sodium and chlorine. that water comes in and pops them off one by one, okay? And then you end up with those ions floating around. So when you've got a salt cube or whatever dissolved, an ionic solid dissolved in water, it is no longer NaCl. It is Na floating around and a Cl floating around, and they're hitched up to those polar molecules. Remember that polar molecules are ones that have a plus side and a minus side, so a partial charge on them because of how those electrons are arranged. You remember we did that when we looked at the VSEPR model stuff, right? It's got those extra electrons hanging out up here, making it real negative, and also oxygen is very electronegative, which means it pulls those electrons, which basically means then that we got a negative side, and then that leaves these protons sort of exposed, giving them a positive side here. That negative hangs out with this positive. This positive will hang out with a negative eventually as they continue to dissolve more and more. Okay? Ionic compounds, acids, and bases. I thought this was a little misleading because, like hydrochloric acid, which is HCl aqueous, is both an ionic compound and a very strong acid. Okay? So I just don't want you guys to think like you got to figure out whether something is an acid or an ionic compound. Lots of ionic compounds are acids because they are ionic and they dissociate very easily in water, and they donate a hydrogen into the mix, okay? And basically that's one of the things. I'll just go ahead and spoiler alert there. I know you guys were waiting desperately to find out, but acids are things that donate protons or hydrogens into the mix, okay? And then bases are things that donate OHs into the mix, okay? So sodium hydroxide, OH, remember, and I could actually stop writing in my book. So we have an NaOH, which is a ionic compound, dissociates into an Na plus and an OH minus. You guys remember that from your polyatomic ion chapter, okay? So I would say that this is an ionic compound and a strong base. And that's not like an opinion. I would point out that this is an ionic compound and a strong base. Okay, so don't think of that as an either or type situation. Okay, good deal. So the attraction between the hydrogen, sorry, not the hydrogen, the polar molecules of water and the pluses and minuses of the crystal lattice, it actually is strong enough to pull that guy out of the crystal lattice, okay? It seems to take a lot of energy to do that. I haven't really gotten into a lot of the math side of that, so I'm just going to take his word for it. He kind of goes into a little bit of numbers right here. I don't think we're going to calculate a lot of that. We're going to do enough numbers a little bit later in the chapter here. So hydration, what is that? That is when water molecules rush in to form cages of molecules around the ions. Okay, and the decrease in electrical potential energy means energy is released, and it balances more or less, he says, the energy absorbed by the dissociation of the crystal lattice. Okay, so just from all of that, you just need to take that hydration is when water molecules form cages of molecules around ions. Oh, and sorry, I I underlined this the other day and I didn't remember that. Okay. Note that the term hydration refers specifically to the ion surrounding process that occurs in water. Other polar solvents act the same way. The more general term for solvent molecules surrounding ions in solution is solvation. Not salvation. Not salivation. Solvation. Okay. Other polar solvents, ammonia, ethanol, methanol. Okay, so nope. These are all underlined again. So at this point we have got dissolution, solvent, solute, soluble, miscible, dissociation, hydration, and solvation. A lot of vocab. So that will likely be some quiz topics there. Okay. All right. We need to note exothermic process. Net flow of energy is out, meaning that it gets hot. Okay. If you remember in our lab, what happened when we added CaCl2, that turns out to be a pretty good exothermic reaction, which is why it boiled and sort of popped. Okay. And endothermic is the drop in solution temperature. Okay. Okay. Let's see. We can read through some of this. Acids or bases dissolve in water. The process is generally highly exothermic. Okay, so that's a good thing to underline here. All right, and this is actually sort of important, and they sort of tell you, so it is standard procedure in every lab, always add a concentrated acid or base to water and never the other way around. Okay, and then you can see why. Okay, the exothermic gets absorbed by a lot of the water, and it doesn't sort of get trapped all in one place. The acid or base remains concentrated, as does the heat released, and in some cases creates explosive fumes such as hydrogen. Okay, so just note that. That shouldn't be too hard for y'all to remember considering what happened. But we will be more careful in the future, for sure. All right. Okay. Net amount of energy absorbed during dissolution is called the heat of solution. Another vocab word. So note that. All right. And then we have another word, electrolytes. Substance that ionize in aqueous solution. Okay. It's not just stuff in Gatorade. Okay. Although, often, it is the stuff in Gatorade. So the things that you're trying to get from Gatorade that your body needs, your nerve cells fire to travel, to send pain signals or touch signals or tingly signals, whatever those nerve cells are doing, heat, cold, those nerves work on, they have little sodium and potassium pumps that doesn't really matter, but they pump the ions around outside of the nerve cell, and then when that nerve cell fires, all of those little ions rush in, and that's what creates a potential, and it sends a little electrical signal, okay? And when you get dehydrated and you don't have enough of those electrolytes, your nerves actually don't fire very well. And then your muscle cells can't do what they need to do, and then you end up with cramps, is the ending result of that. Okay? And so what is the word nomenclature just means how we write things. So the nomenclature the naming convention for heat of solution is that if it's positive, net absorption of heat, which is going to be endothermic, and negative values indicate a net release. Okay, so these are all going to release heat. These are all going to absorb heat. All right, ammonium nitrate, instant cold packs, ammonium nitrate right here. So you can see it's got a pretty big positive number, which means it's going to absorb. Okay. Now, let's talk about entropy. More words here. I'm just throwing a lot of these here. As you're studying for your quiz at some point in the future, you'll probably want to make some note cards or something like that just to get some of these words stuck in your head. Okay. Entropy. It is the measure of the disorder present in a system. Okay, and it's kind of one of those weird abstract concepts that doesn't. There are a couple examples that are pretty intuitive, but then some of the other stuff you're like, I'm not really sure whether that's more disordered or less disordered, or if that's good or that's bad, or if that's higher entropy or lower entropy. So if we just talk about, okay, here, this is perfect. He's got some good examples in here. All right, so he's got order and disorder. And so these are sort of macro level or large high level things of order and disorder, such as cards. Okay, and entropy is not about things being balanced so much or even stacked up so much as it is just about them being in a pattern. And at a high level, this doesn't matter so much because it doesn't really mean anything about those cards for them to be stacked in a particular way or for them to be scattered on the floor. Okay, but what it does matter, sort of quote unquote matter, I guess, in the universe, I would say, is that when things like this happen, you have hot and cold separated, you put them together, and then they both become warm as the heat from here spreads to there. This is like, it's, to me, that's not clear which one of these is more or less disordered. Okay, but on average, when we look at this, this is more disordered than this one. Anytime you have a separation that becomes, or a gradient, a difference in one place and another, anytime you've got a gradient, you have less disorder than when that gradient is eliminated. Okay, and there's a lot that goes into all that. We'll touch on thermodynamics next year in physics, and we'll talk about it some then as well, but now it's not really the place to do it, even though it's a super cool topic. So this is sort of the same thing here. We've got all the gas molecules trapped on one side. This side is perfectly free of it. Well, as soon as you open it up, boom, those gas molecules fill their space. Okay, we know that because gases don't have fixed volumes. They fill any available space that they're given. Okay, and so gas rushes into there, and now it's more disordered than it would. And if you think about it, like, the question is, to figure out if something has more disorder, the question is, would you have to do work to get it back the way it was? And if the answer is yes, it means that you have a more disordered state and you would have to do work to get it to the less disordered state. So what would you have to do? If these were marbles, you'd have to pick them all up and put them back into one container, right? So that you would have to do work to decrease the entropy. You always have to do work to decrease the entropy in a system, okay? And if these are gas molecules, you'd have to push and increase the pressure to make them all go back into one place. You can do it. You just got to put in the work, okay? And we see that this is ordered here as maybe a big crystal of salt, and then it's disordered as those are dissolved in the water or whatever they're dissolved in. Okay? All right. So it's a measure of, this is the technical definition that we will be using, measure of the disorder present in a system. Okay? Just as minimizing energy is one of the universal principles. So we've talked a little bit about that, how doing the least amount of work or settling into the lowest energy state, that's what the universe do. It always does it. It will always find the lowest energy state that it can get to from where it is. Okay? So just like it will minimize energy, it will also maximize entropy. And on a big level, this can mean like everything that can go wrong will go wrong. It can also mean you have to work really hard to increase the order of any particular system. Okay? And so when you are decreasing the entropy in one place by putting all the marbles back into one box, let's say that decreases the total entropy by 100, taking it from scattered everywhere to back into one box. Well, you had to put in 200 in work to make that 100 decrease in entropy. Does that make sense? So we decrease entropy all the time in a given area, right? So we clean up our rooms sometimes. That's increasing the order of your room, but overall, it's contributing to the eventual heat death of the universe by increasing entropy overall. That's a little joke. If we didn't think Jesus was going to come back, we would be forced to reconcile ourselves to the idea that eventually the universe would just become a lukewarm, totally, maximally disordered state in which all the energy was used up, everything was at like 5 or 6 Kelvin, and there was no way for anything to live any longer. So, good thing we're Christians. All right, good deal. A lot of sort of deep concepts there in entropy, which are super cool, but don't have the time. I'd love to talk to you about it for days. Okay. All right, so let's talk about now this other concept, another vocab word, Gibbs free energy. Okay. Which is, so let's just, I'm going to do like he does. He says, if you'll just hang with me for another paragraph or two, you'll see how this works. Okay, so this is a kind of a weird abstract concept, but it helps us predict things, so it's useful. Okay. In any process, there's an increase or decrease in the internal energy of the system and an increase or decrease in the entropy of the system. Okay? They're related together by the Gibbs free energy. Okay? And natural processes proceed in the direction that reduces the Gibbs free energy in the system. Okay? So, and when he says natural processes, he means ones that happen spontaneously. Okay? It means that you don't have to force them to go, they'll go on their own. Okay, so you let go of a tire at the top of a hill and it will roll down that hill without you doing anything else other than starting it. Okay, you give it a little push or put it on its side and just let go of it and it's going to start rolling down the hill. Well, because that's minimizing that, and there's no such thing as Gibbs free energy for like a big thing like a tire. It's just all about internal to molecules and a solution. But it's minimizing that free energy, and at the end of the day, even though it might get some speed, it might do whatever, it's minimizing its energy and maximizing its entropy. And to get that tire to the back to the top of the hill, let's say that gives it 100 joules of potential energy. Well, you've just spent 105 or 110 or 120 to give it that amount of order / energy in its little system. Okay, so you can't beat entropy. It always wins. All right. So what are all these things right here? So pretty simple formula here. Does have some deltas in it though, but those just mean the change, right? So we would literally read this out loud. The change in Gibbs free energy is equal to the change in the heat of solution, or the heat of solution, minus the temperature times the change in the system entropy. Not going to get that the first time because there's too many weird concepts all at once right there. Okay, which is fine. Okay, which is fine. We don't have to know necessarily all about that. We do want to know a couple of things though. The higher the temperature is, so the bigger T is, the greater the subtracted entropy term is compared to the heat of solution. So the bigger T is, the bigger this is, the more you're subtracting from this guy. And at a low temperature, delta H is greater than, so this term is bigger than this term, and G is positive. And when G is positive, such processes do not occur by themselves. Okay? So as that temperature goes up, this gets bigger and bigger, forces this to go negative, and those do happen spontaneously. So at a high enough temperature, this term is bigger than that term, making this one negative when you do the math, and that does go spontaneously. Okay? So sometimes, and this is interesting, and this actually helps explain why solubility works the way it does, right? So you're making sweet tea, and if you want to dissolve a lot of sugar in that tea, because this is Mississippi and that's what we do, you have to make it hot and put the sugar in while it's hot. Well, why is that? Well, sugar solubility is higher when the solution is hot. Why is that? Well, because that has to be a spontaneous process for it to happen, and it only becomes spontaneous when the temperature is high enough. Okay, so at some point, it gets to where you are not reducing the Gibbs free energy anymore, and it stops working, and you can't get any more sugar to dissolve. Okay? All right. Electrolytes. Okay, we see right here. Note that electrolytes in solution conduct electricity. So you can actually tell the purity of water and how many dissolved ions it has. Water often comes with things like magnesium and calcium and iron and stuff ionized in it. And you can see how much it has dissolved in it based on how well it conducts electricity. So more electrolytes, it conducts more electricity. Okay, you guys can read the rest of that yourself. We're running a little long here. Okay, so we want to dissociate so thoroughly. Basically, that means every HCl gets dissociated into H plus and Cl minus. All right, dissociates a lot. It's a strong electrolyte. Okay, strong electrolytes ionize readily, and thus they conduct electricity. Acetic acid, that right here, main component of vinegar, is a weak electrolyte. So when it dissolves in water, most of them end up staying like this. Okay? And they don't become these. Okay? And note right here, normal reaction yields arrow is replaced by a double arrow, meaning that it goes back and forth. So what happens is the rate of dissociation of this molecule this way into these matches the one with these coming back this way to form that one. So it's not, okay, you know, the water molecules walk down the line and say, okay, you dissociate, you dissociate, you dissociate. They're all dissociating and de-dissociating and dissociating again and then undissociating. They're going back and forth, and there's always different ones. But overall, there's always, let's say, 24% of them who have dissociated and 76% that have not at any given temperature. Okay? Which ones are the ones that are dissociated versus together, you can never know because it's all super tiny stuff. Okay? And just because something is soluble in water does not mean it's an electrolyte. That's a good thing to know. Sucrose, which is just regular table sugar, is very soluble, and it participates in hydrogen bonding, so it readily dissolves. But they're not ions. Okay, they don't have a net charge, and because of that, they're not sucrose molecules are not electrolytes. Okay, so that's you just need to know that. Okay, so table sugar, soluble, not ions, no net charge. Sucrose is not an electrolyte. So that's almost like a logic game right there. Just make sure you note that. Okay, I think that's probably going to be good for covering 10.1. Okay, so a lot of conceptual stuff, a lot of stuff that can really only be tested by fill in the blank or short answer or something like that. So just go ahead and start storing those words in your mind. I'm going to send out some additional problems for you to work through to make sure everybody's cool with it. We will have test on Tuesday, and that's really kind of your focus now. I have no idea when I'm going to get the lab reports graded. It will be as quickly as I can. So they take longer to grade because there's actual writing involved, and I've got to put a rubric on every one of them. So just bear with me on that. Don't be worried about it, but just we're going to get there. So focus on your tests, review your quiz, what you got and what you didn't get. If you didn't get it, make sure you can work a problem and get the right answer. Okay, I'm going to try and work every kind of problem that we could have on this test to let you guys have a chance to see what you're missing or not. Okay, I will talk to you guys soon.